SwayamPrabha. Digital India. Educated India.
Hello, this is a course on variational methods in mechanics and design. My name is Ananta Suresh. I am in mechanical engineering at IISc, that is Indian Institute of Science, Bangalore. And here is my email address that anybody who is taking this course can send an email to, and there will be details about my teaching assistant later on for you to also contact. Okay, as you can see the title, first let us understand the words in the title: variational methods in mechanics and design. Here is a book that is a very good book called The Variational Principles of Mechanics by Cornelius Langlois, Doe Publications, that means it is affordable, accessible. And this is about variational principles in mechanics, whereas if you look at the title of the course, it is variational methods in mechanics as well as design. When it comes to variational methods in mechanics, it is very classical in the sense that there are a lot of books that you can read from. The book by Langlois is one good one that I like, that you might also want to refer to. Now let us look at what are variational methods in design. This is something that you do not find even if you Google, but that is what we are going to discuss both in mechanics as well as in design. What I mean by that is that structural optimization, that is the process of optimizing the structures, those problems can be formulated using these so called variational methods. So, variational methods are useful in mechanics and they are also useful in design, because structural optimization, the purpose of that is actually design. So, both structural optimization design as well as mechanics can use what we call variational methods, which is the focus of this course. So, let us ask the question, what are variational methods? In mechanics, we have what we know as vectorial methods. As opposed to vectorial methods, now we are going to discuss variational methods. Okay. Let us first understand what vectorial methods are, and then we will understand what variational methods are. Vectorial methods, what I am showing here in this equation, is that all forces that are acting on a body Fi, where F is a vector, there is F1, F2, Fn, if there are n forces, all of them summing to 0, all of you know what that stands for. That stands for static equilibrium, that is a force balance, right, all the forces that are acting. So, if I take a spring and a mass under static condition, if the spring constant is k and we have a force F acting on it, and we denote the displacement of this mass as x. Okay. In this particular case, if I draw the free body diagram of this mass, which is here, the force which is applied, and k times x, if we assume that this spring is linear, meaning the force exerted by it is proportional to the displacement x, that is k times x is the force that acts this way, because if you try to move the mass to the right, then the spring will be extended and it wants to go back. So, that is the force, the spring force kx, and this force is F. So, this F and this kx balancing each other is the force balance for static equilibrium. Static equilibrium means that mass after this force is applied moves to a new position, which will be determined by this. That new position is given by x equal to F divided by k. That will be the motion or displacement of this mass. In that position, applied force F and this spring force kx will be balancing each other, and that is what we call as vectorial method, where you have forces balancing to become 0, that is when the body will be in equilibrium, whether it is an elastic body, rigid body, any body will be in equilibrium when all forces acting on it are balanced. That means that sum of all those forces, vectorial sum of all those forces is equal to 0, that is what we call vectorial method. Okay. Such a simple problem as this spring and a mass, in fact here we are not even talking about dynamics yet, that is the inertia, that mass we are not included yet, just the statics. Instead of solving it this way, balancing the forces, we can do in a different way, and that is like this, where we have introduced a symbol Pe that stands for potential energy Pe, which is defined in a particular way. Here for this problem it is half kx square, which you recognize as the strain energy stored in the spring. When the spring is pulled by a distance x, then the energy stored in the spring is half kx square, and then we have this Fx, which is F times x, which is the work done by this force F. This is potential energy in this case. This potential energy, if we minimize with respect to this x is the one that we are trying to find. Even in this force balance method, when we balance all the forces, we get an equation. That equation is in this case kx minus F equal to 0 or kx equal to F, then we can solve for x. Instead of solving it in this manner, you can also solve it in this manner. Here we are saying we want to minimize potential energy with respect to x, meaning that x is our variable for minimization. When I do that, then I get an equation that is exactly the same. If you see half kx square and minus Fx, which is the potential energy, if I say I want to minimize it, then I have to make the gradient of it or the derivative of this, that is dPe by dx, I have to make it equal to 0. If I do that, let us take derivative of this. dPe by dx is the derivative of potential energy. Half kx square, when I take derivative, I get kx, because half and this 2 become unity, and then I have kx, k and Fx, if I take derivative, that is going to be f. It is a linear term, this is a quadratic term, this is a quadratic term, and this is a linear term. This will become kx like here minus f like here equal to 0. So, what it is stating is a principle, as opposed to what we have written is like a statement. It says that all forces are balanced and sum of forces equal to 0, vectorial sum of the force equal to 0, whereas here we are saying that potential energy with respect to the variable that we have should be minimized. That is there is a distinct difference between the two approaches. This is the vectorial method and this is the variational method in statics. Okay. So, here when you say forces are balanced, it is something like a fact, because according to laws of motion, if all the forces are balanced with one another, then the body will be at rest or it is in static equilibrium. That is what it says here. Whereas here it says that any system that is at equilibrium will have its potential energy minimum. It is a principle, it is a minimum potential energy principle. That is a difference between these two. Okay. Now, let us take an example of solving this optimization problem. So, what you see here, minimization potential energy with respect to x is an optimization problem. That is why in this course we will be dealing with optimization problems, okay, as opposed to this, which is a law of physics, whereas here we have an optimization problem, which is also a principle. We can call that also a fundamental principle. Now, if I take in the previous example, we had potential energy half kx square Fx. If I take k equal to 10 and F also equal to 10, then I can plot this strain energy half kx square, which is a nice parabola. The red curve that you see here is half kx square, where k I have taken as 10 and x is on the x axis. I am varying that from minus 2 to plus 2, that is a red curve you get. Okay. But what we want is potential energy that also includes this minus Fx. If I plot half kx square minus Fx, then I get the blue curve, and if you see previously the minimum point was at x equal to 0, meaning that if there is no force, the spring will stay put where it is, there will not be any displacement. The moment I apply some force F, in this case I have taken F equal to 10 units, okay. K is 10 Newton per meter, F is 10 Newtons. If I put that, then the curve becomes this, and now here at x equal to 1, because x equilibrium value is going to be F by K, 10 by 10 equal to 1. At x equal to 1, I have a minimum point. That is what this principle says. It says that when you minimize potential energy, I get the answer for my x. I do not have to think in terms of forces, I can think in terms of energy. That is what is the basic thing for variational methods. And if you think about a vectorial method, where the force is a vector, you have to take care of the vector, whether it is 1 dimension, 2 dimensions, 3 dimensions, you have to take all the forces as vectors and sum them vectorially to get the balance equation, which is the force equilibrium static equilibrium equation. Here we have a scalar, not a vector, potential energy, whether it is 1 dimension, 2 dimension, 3 dimensions, any dimension, whether it is rigid or elastic, this potential energy will always be a scalar. That scalar quantity is being minimized with respect to the variable that you want to find, and you get the answer that way by solving an optimization problem. So, if I have a little bead and I leave it anywhere, it is going to come back here, because that is a minimum point, it will be stable. Once it is here, when I perturb it, it is going to move back and just return to that equilibrium position. That is, stable equilibrium is given by minimizing the potential energy. Okay. So, it is an optimization problem, that is what we should remember in the case of variational methods. Now, let us move on from static equilibrium to dynamic equilibrium. So, in this case also we have vectorial method, which I am showing in blue color here, F equal to ma, Newton's second law, everybody knows that, right. Force is a vector here, acceleration a vector. In one dimension I am not showing this as a vector, but it has a particular direction, F equal to ma, or I can write it as d by dt of mv. M, we assume that it does not vary with time, okay. It could vary, and v here is the velocity, derivative of that will be acceleration here, okay. F equal to ma, everybody knows that Newton's second law. This is a vectorial method. We are basically looking at the inertia force ma and applied force F balancing each other is our vectorial way of doing dynamics, okay. There is a alternative to this, just like we had an alternative to do static equilibrium. And how did it start? Newton had a contemporary called Leibniz. Leibniz was in France and Newton was in England. Newton was doing this vectorial method, which had his Newton's second law. Everybody has to obey that law to do mechanics calculations. Leibniz had an alternative view. So, here you have force, and what Galileo and Newton everybody found was that effect of force, the cause of the force is the cause and acceleration is the consequence. There is a causal relationship here. As opposed to that, Leibniz and Bernoulli and some of these other people came up with this principle. Later, of course, it culminated in what is called Hamilton's principle, which will give you exactly the same equation. Okay. We are extremizing a quantity which looks like this, integral from 0 to t half m dx by dt square plus fx dt, extremized with respect to xt. Just like in the previous problem where we minimized, here we are leaving it open. We can maximize it or minimize it with respect to x of t, that is our unknown. Dx by dt would be our velocity, d square x by dt square will be our acceleration. So, we extremize a quantity, and that is called the Hamilton's principle, which is a variational principle. As you can see, we all understand F equal to ma without much trouble, whereas if you look at this, it is quite analytical, right, because there is an integral which looks complicated when you see it for the first time, and you are solving an optimization problem. So, you are extremizing a quantity with respect to x, an integral you are extremizing with respect to x t, that is you need to find x t such that this quantity is extremized meaning compared to other x of t's in the nearby. Okay. Let us say we take a particular x t, that is let us call it x star t. In the vicinity of x star, if you look at other functions, you substitute them here, then what you find is that at x star it will have either the least value, minimum value or a maximum value in the vicinity. That is what Hamilton's principle says. Okay. It is a very profound thing. After Newton's second law was proposed, having an alternative to it, it came much later when Hamilton came, but ideas were there. Ideas were there from Leibniz, Bernoulli and Euler, Lagrange, all these people, and that culminated in the Hamilton's principle, which is an alternative to Newton's second law. Okay. If you look at this, this is more of a causality is here, there is a force and hence there is acceleration of the body, whereas here there is a sense of purpose, right. You are extremizing something, meaning that there is a purpose, that is there is a goal, there is an objective function. Whenever there is an objective function or an aim, that is an optimization problem, because we have a quantity that is extremized with respect to x of t. So, there is a sense of purpose. If I take let us say an object, okay. So, let us see if I have an object. Well, I have a pen drive. If I drop it, right, you all know that it is going to fall down. We can say that there is gravitational force which is accelerating this pen drive and hence it falls. The other way of saying is that this particular body, in this case this pen drive, wants to fall because it wants to extremize its a quantity that we call an action integral. We have an integral here which is an action integral, right. This action integral needs to be extremized and that is why it is going to fall, right. So, that is the alternate view. There is a purpose, there is an objective and hence this also is a optimization problem, but this has a different name. This is called a calculus of variations problem. Okay. Calculus of variations, everybody knows ordinary calculus of functions. Here we have calculus of variations. That variation is what we need to understand. What that means is that when you have a quantity, you are looking at quantity for varying values of the function, meaning that actually different functions, not just varying values, it is just there is x1 t, x2 t, x3 t, x star t, several functions are there. You are selecting one of them to extremize a quantity. Okay. For that you need to understand the concept of the variations. So, in this course what we will focus on will be optimization problem first. Okay. So, in the lecture 1 we are going to talk about optimization problems of two kinds. Actually there are several kinds, we will focus on two kinds. One is in finite number of variables, other will be in terms of functions. So, let us look at classification of optimization problems and the place of our topic, which is calculus of variations, because that variations word is what is there in our course title, variational methods in mechanics and design, and that is why we will focus on calculus of variations. Okay. So, if you look at what we are going to discuss now, you first have to understand the spirit of optimization, and then we have to understand what makes a good optimization problem or even optimization problem without the adjective good. We look at a number of types of optimization problems, in particular finite variable optimization and then calculus of variations. This is what we want to focus on, but you need to understand how it is different from finite variable optimization. We will learn a number of things. First of all, we will understand philosophically and mathematically, analytically what optimization means, and then we want to be able to distinguish among the different types of problems, optimization problems, what are the similarities, what are the differences, and we will consider some examples so that we are able to appreciate the difference between finite variable optimization and then calculus of variation problem. So, what is the spirit of optimization? Optimization basically says that you achieve what is best with what you have. because life is full of constraints. All resources are limited. Whatever is a good resource, it is limited in quantity, but we always want to do the best that we can, right. So, we do that in our daily lives as well, doing the best that we can with what we have. That is what is optimization. In fact, the word optimization, people say, has evolved from optimism. Okay. Optimism meaning that you hope for the best always, right. And in structural optimization in mechanics, there is a sense of minimization, maximization that makes it very mathematical and hence amenable for computation in the computer. Okay. And in order to understand optimization, there is a witty way of saying it, what I have said here, optimization hinders evolution. When you take some situation or an object, you keep on improving it and improving it, eventually it will evolve to the best, that is optimum. But if you do optimization problem right at the beginning, you will bypass this entire evolution. So, optimization hinders evolution. You can say nature has the best solutions, but it has the best solutions because all the ones that are not good have been eliminated, what we call survival of the fittest. Only the best ones survive, that is evolution, right. So, instead of evolution, if nature had a way of doing optimization, all of a sudden it would have achieved the best, which is not possible in nature, but whereas in the engineered world that humankind can actually make this happen. Okay. And everything is in a way optimized. When something is not the best, we modify it to make it better and better and better, and hence we achieve the optimization. Okay. That is the spirit of optimization. What do you need to do optimization? Most important is the objective function. You should have a purpose, you have an objective, you have a goal. Just like in the variational methods, a body that is dropped falls because it has a sense of purpose, it wants to minimize its potential energy, okay, or extremize this action integral. Similarly, when you want to do optimization, you should have a purpose, an objective function. The most important one that you need, you make it the objective function. When you want to improve that objective function, you need some variables to play with, and those are the optimization variables, or the, if you are doing a design problem, there will be design variables. So, those you need, those are the ones that are going to adjust in order to achieve the best. As I said, there will always be constraints, okay, constraints that actually constrain you. They can be bounds on the variables, they can be things that decide the performance of the situation or an object that you have in mind. Okay. There will be a lot of constraints. Those constraints can be equalities, inequalities, linear, nonlinear, all of those variants. Okay. And you also need some method to compute the objective function and constraints whenever the variables are known. Okay. That is something you need to do to optimization. It should all be mathematical, and there will be some other constraints or some other variables too, which we call subsidiary variables or state variables. Okay. These also will be there in our optimization problem. Whenever you want to do optimization in our daily life, we always say casually that I want to optimize it or I have optimized, but what we really need to understand is that real optimization needs to be mathematical. You need to have variables and objective function and constraints expressed in terms of that variable or variables, and there will be, in addition to the design variable optimization variables, there will be subsidiary variables or state variables in every given problem. Okay. So, let us take a couple of simple examples, because we will begin at something very basic. If you look at the function 2x and you want to say I want to maximize f equal to 2x, there is no fun in it, because as you increase x, okay, this is not x factorial by the way, the exclamation mark. Okay. As you increase x, f is going to increase. So, you can take x to infinity, f goes to infinity. That is not a fun optimization problem. Okay. If you want to maximize this f of f equal to 2x subject to a constraint like this, x square plus y square minus 4 is less than or equal to 0, then it is somewhat interesting, because this one limits you, like even if you take let us say y equal to 0 here. Okay, there y can also vary as a problem, as a variable. If y equal to 0, if you take, x square minus 4 less than or equal to 0, that limits x to plus or minus 2, right. So, you want to maximize it, you can go up to 2 times x equal to 2, 4, that is the best, right. Here in the first one when you say 2x, you can go to infinity, right, x can go to infinity, but here we are restraining x from going to infinity. Okay. So, for a good optimization problem which is this, where there is a maximum or a value that is best, that needs a constraint. There should be something opposing, you want to maximize f, but there is a constraint. So, if there is a conflict between the objective function and constraint, that is optimization. Okay. There should be a conflict. The conflict can be a single function too. So, f equal to 2x minus x square, if I take, I want to let us say maximize this. Okay. As I increase x, 2x increases, I can make it very large, but as I increase x, this x square is also going to increase, and that is being subtracted. So, f is going to go down. So, as I increase x, it is not guaranteed that this f will always increase, right. So, there is a conflict, if I increase x, this increases, first term increases, second term along with the minus sign will decrease. So, there is a conflict. So, conflict can be there between objective function and a constraint, or within the objective function different terms can compete with each other as x is varied. Okay. And that is the optimization spirit, in the sense that there must be conflict, you resolve the conflict and find the best. That is what we do in optimization. Okay. And that is what is being shown here. In this plot we have x on the x axis, 2x minus x square on the y axis. So, I have this maximum at that point x equal to 1, and that is what we get here. Okay. There is a conflict. If you look at this function now, it is non-monotonic, meaning it is monotonic means that it keeps on increasing or keeps on decreasing, like monotonous life, there is no change. Now, this is non-monotonic, it increases first, achieves the maximum and then decreases. So, that is interesting because there you have an optimum, in this case a maximum. Okay. And if you think about our course focus, one is mechanics, I already discussed that there is optimization, there is sense of purpose for both static equilibrium to minimize potential energy and extremizing action integral in the case of dynamics. If you think in terms of design, is there conflict in structural optimization? There is plenty of conflict, right. We would like to build a structure with as minimum material, as low amount of material as possible, while we want to make it very stiff, we want to make it very strong, we want to make it very stable, we want it to be many other things. Okay. But then you cannot make something stiff with little material. So, you have to optimize the structural design to get there. So, there is lot of conflict in structural optimization, there is competing. Lighter structure with high natural frequency, there is a conflict. A flexible structure that is very strong, there is conflict there. A structure that is subject to multiple loads, again there will be conflict between, if you apply this load versus that load, there will be conflict between those, or multiple loads are there, conflict among them. So, there is enough conflict in structure optimization or in designing structures. That is what we will analyze in this course, what conflict is there and how to resolve that conflict using optimization. A typical optimization problem looks like this. There is an objective function and you minimize or maximize with respect to some variables subject to some constraints and some limits on the variables. Here is a symbolic form of that. We are minimizing a function of two variables x1, x2, those are your optimization variables subject to some constraints. It is an equality constraint in two variables, it is an inequality constraint in two variables, some additional constraints like lower bounds and upper bounds on the two variables. These are the limits on the variables. These are typical optimization statement. Here if you notice, the variables are finite, that means that there is x1 and x2, two variables. Okay. If you look at structural optimization problem, you have minimized some objective function which will be in terms of variables, optimization variables and the state variables, what we call subsidiary variables couple of slides back, additional variables will be there. Usually displacement, strain, stresses and temperature, electric potential, all those are state variables. There will be constraints on the state variables which will be governing equations, constraints on resources like weight, cost, size, etc. Constraints on performance for stiffness, strength, frequency, buckling load, all those are constrained performance, the limits on the variables, and what you consider data will be material properties, loads and so forth. Okay. This is how a typical optimization problem looks like. This one can be like a finite variable optimization or calculus of variations. So, what we will consider in this course once again to summarize is how we look at alternative to classical way of doing vectorial mechanics or vectorial methods, where for static equilibrium you balance forces and for dynamic equilibrium you use Newton's second law. Here we have a alternative which will be rooted in what is called variational methods, which are basically optimization problems where there is again a sense of purpose. There is an objective function that all living things or inanimate things try to achieve. Okay. That is the thing that we need to remember, and then when we continue in the next lecture, next half of the lecture, we will look at the classification of the optimization problems. Thank you.